we are ready to go. So today we're going to continue on with our look at hypothesis testing, and this is where we are going to basically stay for the rest of this semester. So we finally developed all the skills that we need in order to do hypothesis testing, and this is the big cool stuff that statistics is made for, that statistics allows us to do in psychology, where we can actually take a look at real situations, real data, and run some real statistical tests. So from now to the end of the semester, basically all we're going to be doing is hypothesis testing. And as we go through, we're going to start off with some artificial situations, such as the one that we'll be looking at today. And then we're just going to keep increasing the realism of those until we get to actual real statistical tests that you will use as a psychologist, either in your professional work or very soon maybe in your advanced lab. And that's what we'll do, just variations depending upon the situation will be the rest of the semester. So today what we're going to continue on is we're going to have a recap of the logic of hypothesis testing, and then we're going to take another perspective for the logic of hypothesis testing. So it's very important to eventually know what it is that we're doing when we're doing a hypothesis test. What is the logic behind it? What is the reasoning behind it? Why does it work as a way of generalizing from a sample to a population? But sometimes it requires multiple views. So we're going to take another view of the way that we looked at it before. We're going to take a new look at it from a different point of view. And then we're going to go through the actual hypothesis testing procedure. We're going to take a look at the self-esteem and physical education program example that we teased last time. And then we'll do some in-class demos, and we'll see if we can get to Harlow and Zimmerman when they did their studies on infant attachment and the infant monkey. We'll see what statistical tests they would have used in that situation, and we're going to do that today. So just a recap of what we're trying to do here. So hypothesis testing, this is important to remember. Hypothesis testing is always about getting conclusions about the population. So we don't need hypothesis testing to get conclusions about a sample, because we can just measure the sample. If we want to know, did the sample improve, we can just measure the sample compared to its previous scores, and that's, either greater than or less than. Did it go up or did it go down? Hypothesis testing is all about going from that sample to the population, so it's always about the population, seeing if what happened to the sample actually applies to the population. And in this case, you want to reach conclusions about a particular population, but it's going to be based on a single sample that we looked at. And in your textbook, they start you off with a sample of 1, but we're going to start off with larger than 1 samples. So for example, today we're going to take a look at a sample of 16, sample of 9, so on and so forth. And very importantly, remember that we are now, in hypothesis testing, going to be dealing with 3 distributions. So we have our sample distribution. These are the subjects that we ran. These are the raw scores that we have. They form their own distribution. We want to be able to get 2 conclusions about the population distribution. So we want to know things about the population. But the way that we get through to the population distribution is by going through the sampling distribution, that distribution of sample means. So we can go from here to here, but the doorway is to go through the distribution of sample means. So once again, what we want to know, what we're trying to do here, the logic of hypothesis testing, the question we want to answer is, if we could apply a treatment to an entire population, what would that do? Would it change the population, in which case we now end up with a new treated population? Or would it do nothing, in which case we end up with the same old previous population? So that's all we're trying to do in hypothesis testing. What does the treatment do? Does it do nothing, in which case you're stuck with the old, in this case, known population? Or does it do something, in which case you transform this population into a treated population? So that's what we want to do. We can never test the entire population. That is usually not possible. So what we do is we take a sample from that known population and we treat it, and then we measure that sample after treatment. So one of the bizarre things to kind of introduce this idea is that we don't measure the sample before treatment. Don't let that bother you, that's just there for educational purposes. It's not what we would typically do. Usually we would measure a sample before and after treatment, but for now we're just measuring it after treatment. So we treat the sample, we measure it, we get its mean, and then we simply ask ourselves, using this hypothesis testing procedure, that sample, has it been transformed enough so that it no longer belongs to the old population, but it now belongs to this new population? It now belongs to the new treated population. So that's what we're trying to get to. And the assumptions that we're making at this time are a little restrictive, but they make the logic a little easier. First off, we're assuming that we're dealing with a known population, right? So one of the easiest examples of a known population is IQ scores. In America, we know that the IQ scores have a mean of 100 and a standard deviation of 15. We know that for the population. Usually we don't have this information, but for the purposes of just introducing it, we do. So we have a known population. We treat it. We have no idea what the treatment does. So the treated population is unknown, right? We don't know what the mean is. It could be anything, right? We could have gone up, we could have gone down. We don't know what happened to the treated population. But we do make one more assumption just to make the math easy, and that is that the standard deviation of the treated population equals the standard deviation of the known population. And what that means is that your treatment affects everybody equally. So if we had an IQ pill, it brings everybody up 20 points. It doesn't work better for people with low IQs. It doesn't work better for people with high IQs. Everybody gets the same effect. Everybody gets moved up the same amount. And that's just an assumption that makes the math incredibly easier. So what do we have in this scenario? Well, remember we didn't measure our sample before we treated it. So we don't have that information. And we don't know what the treated population is, so we don't have that information either. What we have is we have our treated sample, we can measure that, and we have information about our original population, our untreated population. We have information about our known population. So our second look at hypothesis, the logic of hypothesis testing, is just going to focus on those two pieces of information that we have. All right, so we're going to move them so that this makes a little bit more visual sense. So this is your known population. You know the mean, so we know where the mean of that population is, and we can measure the mean of our sample that we treated, so we know where the mean is, and there's going to be a difference there. And the question that we're asking or answering using hypothesis testing is, what does that difference mean? Does that difference mean that this sample does not belong to the the known population? Does that difference, is it big enough to indicate that this sample no longer belongs to the known population? Or is the sample small enough to suggest that it still belongs to the known population? That's what we're looking for. Is it big enough to say, no, the sample no longer belongs? Or is it small enough to say, yes, the sample still belongs? So how do we make that decision? Well, this sample could have different likelihoods of coming from this population. So just to kind of reiterate what I just mentioned, if the sample still belongs to the known population, right? So if we make the decision that this sample belongs to the known population, that means that the treatment didn't do anything. It started off as a part of the known population. We treated it. It's still part of the known population. We haven't changed this sample at all. Still belongs to the known population. If that's the case, then we accept the null hypothesis. We accept the idea that our treatment does zero. Our treatment does nothing. So if we decide that our sample after treatment still belongs to the old population, we conclude our treatment does absolutely nothing. If, on the other hand, because of this difference, if it's big enough that we decide that this sample no longer belongs to the known population, but must now belong to a treated population, then our conclusion is, well, we've changed this sample. It used to belong to the known population, but we treated it and we've changed it enough, so our treatment does something. Our treatment changed this sample. They belong to a new population, and in that case, we reject the null hypothesis. So at this point, I'll just point out that the book is kind of a stickler for accepting the null hypothesis or rejecting the null hypothesis. Typically, that's what you do. You accept the null or you reject the null, and you don't really worry about the research hypothesis. That's technically the way that this works. However, for practical purposes, which is what we're really concerned with in this course, if you accept the null hypothesis, you reject the research hypothesis. If you reject the null hypothesis, you accept the research hypothesis. And we're just going to use that kind of terminology because otherwise, and you'll find this in your textbook, you get into massive double and triple negatives. So if you have the null hypothesis, that's a negative, right? The null hypothesis. If you reject the null hypothesis, that's a double negative. If you fail to reject the null hypothesis, now you're dealing with a triple negative, and that gets pretty confusing. So I'm fine with you saying, oh, we accept the research hypothesis, or we reject, the research hypothesis. That's fine in this class, but just be aware that it's technically not true, and if you say it to a statistician, you might get, reprimanded, but it's splitting hairs. We want to understand what's going on, so we're going to keep it with rejecting and accepting either or. But the big point is, though, if you reject the null hypothesis, you accept the research hypothesis. If you reject the research hypothesis, you accept the null hypothesis. You reject one, and you accept the other. All right, so if we reject the null hypothesis, it's because our treatment does something. So that's what we want to know. What population does this sample now belong to? Now that we've treated it, what population does it belong to? And all that we have access to is that difference right there. All that we have access to is how big is the difference between the mean that we measured in our sample and the mean that we know for our population. And that difference here can give us a probability that this sample still belongs to the known population. And that's what we're going to be figuring out. Yep?
Did you say that we don't normally know the known population?
Typically, yeah.
So then what would we do?
Well, what we're going to do is, as we get into more realistic situations, what you'll find, the general move is you use the sample to assume or to predict things about the population. So in order to figure out the standard deviation, we look at the sample standard deviation. And then sometimes the known population, its mean is driven by hypothesis. Sometimes it's driven by the sample, but we do estimate it in certain ways, but that adds like another level of complexity. All right, so we want to know, basically, does this belong to this population over here? And what we can do is we can say, not whether it belongs, but what's the probability that it belongs to this population over here? In other words, what's the probability of getting this sample mean if your population has this population mean? And that's what we do in hypothesis testing. So that's why we were looking at the properties of samples and populations. That's why we were looking at how the relation between samples and populations are, because if you take a look at the relation between a population and its sample, usually a sample, if you take, for example, 5 subjects and you calculate their mean, that sample came from this population, right? And that mean for the sample lines up with the mean of the population. So this sample mean lines up with the population mean. And as we saw before, this sample is highly likely to occur, right? This sample mean is highly likely to occur. If you picked those 5 people out from this population, you would not be surprised. You would kind of be like, that's kind of what I expected. You know, if we go back to the example of the IQ Olympics, you know, that's kind of what we expected. Some people that are, you know, somewhat below average intelligence, some people that are somewhat above average intelligence, one person that's at average intelligence. You would expect that. It's a different story when you get a sample mean that is further from the population mean. So if we got a sample mean that looked like this, right, and it was way below where the population mean was, that can only happen if you get a sample from the edges. And it is, or the tail, and it is way less likely to get this sample over here. It's way less likely to pick people from the tail because there's fewer people from the tail. But the only way you can get this mean is by choosing people from the tail. So we would assign this sample a lower probability. And we saw this again intuitively with the IQ Olympics example, because if the first person that you get is Neil deGrasse Tyson, and the second person that you get is Bill Nye the Science Guy, and the third person that you get is Bill Gates, and then you get, I forgot the mathematician, but the Oxford teenage mathematics wizard, and then you get Marilyn Bon Savant over here. If you get 5 extreme cases like that, sure, they're from the population, and they will give you a sample mean that is pretty far from your population mean, but it's also highly unlikely that that would happen. It's very unlikely that that would occur. And that's what we're doing in population testing. Hypothesis testing. We take a look at where the mean is for your known population. You take a look at where the mean is for your sample. Those are the two things we can measure. You take a look at the difference, and then we're just gonna figure out what are the chances that this mean over here could have been produced by taking people from this population. Because there's always a chance, right? It's always possible that you could have picked 5 people from the extreme tail, and that's what created your sample. However, this is highly unlikely to have occurred. And depending upon how likely or unlikely your sample is to come from the population, that's how we make our decision. So we were talking about likely and unlikely. So what is it that we're doing about this? So what we do is we use this difference here to figure out the probability that this sample came from that population. And it's important to remember that there's always a chance, right? It's always possible that your treatment did nothing, but you still have a big difference between your population mean and your sample mean just because you chose unique people from your sample, weird and wonderful people from your population, right? You chose extreme people randomly, there's a chance, from your population. So what we do is if this sample here is likely to have come from the population, if it's highly likely that you could have chosen a sample that produced this difference that you saw, well then we say that the treatment hasn't done anything, right? That your sample still probably belongs to the untreated population, and we accept the null hypothesis. If, on the other hand, we take a look at this difference, and we say, sure, it's possible, it's within the realm of possibility that our sample could have come from our untreated known population, but that's highly unlikely. It's unlikely that this could have occurred by chance. The only other alternative is that it's likely that your treatment does something. So if it's unlikely that you would have gotten your sample by chance, the only thing left is that it must have been your treatment. Your treatment must have changed these individuals, and we reject the null hypothesis, and we accept the research hypothesis. So the last thing we need to address is, well, how likely is likely? What is this level of likelihood that we are going to use? Another way of thinking about this is, what is the line in the sand? So hypothesis testing, you can think of it as a line in the sand, where you have a sample and you have a line on your distribution. And it's almost like, if there's any parents out there, or if you were these children, it's like when you're riding in the backseat of the car and the children are fighting, and the parents say, all right, the first person that crosses this midline, you're gonna get into trouble. They drew a line in the sand. And you can get as close to that midline as you want, and you're not going to get into trouble. But as soon as you cross it, you do get into trouble. That's what we do. We have a line in the sand, and we tell that mean, we tell that sample mean, we say, don't cross that. You cross that line, and I'm going to reject the null hypothesis, and then we just see, does it cross the line or does it not cross the line? That's what we do. So that's how we define likely. And in the actual procedure, the level of likelihood is your alpha level. That is given to you in your question. Alpha level is something that you will not touch, you will not change, you will not mess with until you get some more letters after your name. All right, so you don't get to choose alpha until you got at least a master's degree, and then maybe probably even you need a PhD. And even then, it's usually decided for you. So anyways, alpha is your probability level. If the probability that your sample came from the known population is greater than your alpha level, and I'll just write the most common alpha level that is used in psychology is 5%. So the most common alpha level, let's see, green is working here. The most common alpha level is 5%, or 0.05, right? It's written both ways. That's the most common alpha level. So if the probability of your sample coming from the population is greater than 5%, then we say, you know what, the treatment did nothing. We're going to accept the null hypothesis, back to the drawing board, our treatment doesn't do anything. If, however, the probability of this is less than alpha, if we figure out our sample mean and we say, you know what, there's only a 2% chance that we would have chosen a sample from this population that produces a sample mean like that. 2% chance that we would have chosen a sample randomly equals 98% chance that our treatment does something. Less than alpha, we reject the null hypothesis, and we say that our treatment does do something. So that's the idea. We're trying to figure out where does our population, where does our sample come from by figuring out how likely is it to go, to still belong to the population. If the probability is greater than your alpha level, we conclude that the treatment does nothing, that your sample still belongs to the population. It's too likely to still belong to the population for us to conclude that our treatment does nothing. We accept does something, we accept the null hypothesis. If, on the other hand, the probability of your sample still belonging to the population is less than alpha, we say, well, it's still possible, but it's pushing the realm of possibility, so it must be that our treatment does something, and we reject the null hypothesis. Incidentally, if you're interested, there is a ton of research as to why 0.5 was chosen. So you might think, well, that's kind of low, right? I mean, only 5% chance. You know, why wouldn't we have it higher? And it really has to do with just human psychology. And my best sort of analogy of where this comes from, if you do an experiment, if you do the following experiment on a group of people, and you tell them that you have a coin, right? So you show them a coin, and you tell them, I want you to determine if this is fair or this is not fair. So we're going to play a game, we're going to flip this coin, and I just want you to determine whether it's a fair coin or it's not a fair coin. And they're like, okay. So you say, all right, we'll flip the coin. If it comes up heads, I win. If it comes up tails, you lose. And you tell me when you kind of feel that something funny might be going on. They're like, all right. So you flip it and it comes up heads. They lost the first round. How many of you would say, that's an unfair coin? I'm calling shenanigans right now. Nobody, right? Because it doesn't seem unbelievable yet. You flip it again, heads comes up again. 2 heads in a row. How many of you would now say, that's a unfair coin? You're cheating. Once again, nobody. So you flip it 3 times, 3 heads in a row, right? Now all of a sudden it starts to dawn on you a little bit. It starts to dawn on you, and you're kind of saying, well, 3 heads in a row, that's happened to me before. I've seen that. It's still possible. But I'm getting suspicious. But I'm not suspicious enough yet to say that's got to be a fake coin. You flip it again 4 times in a row. Now you're getting even closer to that line. You're getting even closer to that line of unbelievability. And the key is that a fair coin, a really fair coin, could go 10 heads in a row. A fair coin could go 20 heads in a row. A fair coin could go 100 heads in a row and still be a fair coin. It's just that you have that run of bad luck. However, the probability that that would occur gets lower and lower and lower the more heads in a row that you have. And what they found is that the average probability where people say that coin is not fair is right around 5%. So if you do this right around, I think it's like 6 or 7 flips in a row, is when people will finally say, you know what, that's enough, I don't believe it anymore, your coin is unfair. So it does have a psychological basis to it, but that, importantly for us though, that's usually the line we're going to choose. 5% is the line, 5% is your line in the sand. Go, if your probability goes below 5%, we say that's way too unlikely for the treatment to have done nothing. So we accept the research hypothesis. If your probability stays above 5%, we say, well, you know, it still could come from the untreated population. We're going to accept our null hypothesis. All right, so that's the hypothesis testing logic. And maybe it makes sense to you right now. Hopefully it does. If it doesn't, it'll eventually sink in. But now we're going to turn from the logic of it to the actual hypothesis testing procedure. And this, for sure, you can do in the next class or two. So this is a procedure. This is a step-by-step procedure. It's literally a recipe for a hypothesis testing. So you might know how to bake bread. You might not know anything about yeast. You might not know anything about the gluten structure. You might not know anything about what kneading the dough actually does to like the bonds in bread, but you can still bake amazing bread. You might not know what's going on underneath, but you can still do a hypothesis test. So these are the 5 steps. We're going to take a look at each of those 5 steps now in a little bit more detail than we did last time. Starting off with step number 1, restate your question as a research hypothesis and a null hypothesis about the population. This is how we go from a question that we're interested in to a question that can be applied, the statistics can be applied to. Because usually we just want to know, is there a difference between a treated population and an untreated population? Is there a difference between autistic children that went through this program versus autistic children that went through a traditional program? Is there a difference between depressed people that took this drug versus depressed people that took another drug? That's usually what we want to know. Is there a difference between these 2 populations? That can't be tested statistically. What we need to do is we need to get it down to 2 possibilities. One is the research hypothesis and the other one is the null hypothesis. The research hypothesis is that your treatment does have an effect. Your treatment does something. And that is written out as the mean of your treated population does not equal the mean of your untreated population. And notice that this is a bidirectional, 2-way research hypothesis. We're going to start with this one. There is another version of it. But this one covers your treatment makes things better, and it also covers your treatment makes things worse. It covers your treatment increases scores, and it also covers your treatment decreases scores. Because if your treatment increases scores, then your treated population will not have the same mean as your untreated population. Fits the research hypothesis. If your treatment decreases scores, same thing. Your treated population will not have the same mean as your untreated population. Also fits the research hypothesis. So this covers 2 possibilities, that the scores will go up and that the scores will go down. There's only one possibility left, that the scores will stay the same, and that's your null hypothesis. So your null hypothesis is that the treatment has no effect, and that is written out as the mean of your treated population equals the mean of your untreated population. So you've given people the treatment, and it's done nothing. Their scores have stayed exactly the same. Population has not changed. And that's what we're going to be deciding between. Is the truth the null hypothesis, so that your treatment has no effect, or is it the research hypothesis that your treatment actually does something? All right, step 2, determine the characteristics of the comparison distribution. So the comparison distribution, and this is my big pet peeve with the book, the comparison distribution is not the population. You do not compare your sample to a population, because a population is a distribution of individuals, and your sample is a distribution, your sample, let me say that again. Your population is a distribution of single scores. Your sample mean is a combination of scores. And you cannot correctly compare single scores to a combination of scores. It would be like playing basketball, where you have to play with just one person and the other team gets a team of 5, right? It's not fair. You can't compare the skills of 5 people compared to one person, right? It's just not a fair comparison. You cannot compare your sample mean to individual population scores. So this is what I hate about the textbook, because the textbook makes you do this for the first few chapters, because it gets in a little loophole by using a sample size of 1, where you can compare an individual to a population of individuals. But we're gonna learn it straight and correct from the get-go. So we need a comparison distribution that we can compare our sample to. And the comparison distribution is the distribution that stands in for your population. It's a distribution that you could compare your sample mean to, right? So we have a sample mean, and we didn't want to compare it to a distribution, a fair distribution. We have our sample mean, we want to compare it to a distribution of sample means. And that's your comparison distribution, that distribution of sample means. So you can see how important it is that this distribution of sample means, all of the possible samples means that can be taken from a population, you can see how important it is that that distribution of sample means, as you increase your sample size, turns into a normal distribution. Because if it didn't, we couldn't do statistics. We would be limited. But we know that when we take our sample and we compare it to the distribution, we know we're comparing it to a distribution of sample means, because we're looking at a sample, compare it to sample means. That's a fair distribution. Compared to your population, number 1, unfair. It's a team of 5 playing a team of 1. Number 2, we don't know what your population looks like. Could look like anything. So we can't even go to table number 1. So just keep that in mind, because they're going to teach you the wrong way first, and then they're going to try to correct it in chapter 6. So I'm going to try to teach you the right way first. We are comparing our sample mean to a fair distribution. We're comparing our sample mean to a distribution of sample means. It's unfair to compare it to the population. So just keep that in mind. So that's step 2. Step 3 is set a cutoff sample score or critical value. This is on your distribution of sample means, right? We have our normally distributed distribution of sample means that has a sample mean there. We're going to draw lines in the sand. And those lines in the sand are going to define these tails known as critical areas. Those are the lines in the sand. That's the target against which we're going to compare our sample. So we're going to find out where our sample is on this distribution. And we're going to see, just like those parents looking in the backseat of the car, we're going to see if it crosses the line. We're going to see if it goes past that middle point, except we draw our middle point somewhere, in the tails over here. So that's what we're going to do for step 4. We set off that cutoff sample score. Step 3. Step 4, we find out where our sample is. So our sample is either going to be somewhere in here, right? So our sample mean is either going to be somewhere in the body, or our sample mean is going to cross that line, like a disobedient child. It's going to cross that line, and it's going to go into the critical value. Step 4 is about finding out where it is on that comparison distribution. So we're going to do that by using z-scores. So z-scores are going to be the way that we can access that table, so we can find out where our sample score is. And then finally, once we do that, step number 5, we decide whether to accept or reject the null hypothesis. We're going to find out where our sample is compared to our cutoff lines in the sand. And if your sample z-score, if your sample goes beyond your cutoff scores, beyond your line in the sand, then we say we're going to accept the research hypothesis. and we're going to reject the null hypothesis. If, on the other hand, your sample is within the cutoff scores, then we do the opposite. We accept the null hypothesis and we reject the research hypothesis. And if this is starting to sink in, if this is starting to make sense, you might have realized that this line in the sand here cuts this distribution into highly unlikely samples, right? Bill Gates, Bill Nye the Science Guy, Marilyn von Savant, or highly likely samples, right? This is the area of highly likely samples. That's all that the line in the sand does, and that's why we make the conclusions that we're going to make. All right, so that is the last of the abstract kind of overview of this. Let's do a hypothesis test. So we're going back to the school. We're now going to take a look at how we would analyze data that we could have picked up from testing these children. So if we go into this school and they want us to increase the self-esteem of their students, and we might notice that they have a very traditional physical education program. And we've been working on a treatment. We've been working on a new way of teaching physical education using games that could increase the self-esteem of these children. So what we're going to do is we're going to put these children, this sample, into the games program, and we're going to compare how they end up, what's their self-esteem at the end of the program. We're going to compare it to the population of students in America. We're going to compare it to, in this case, the known population of students in America. And we're going to see if our sample difference is big enough to indicate that our students no longer belong to the known population of students that are doing traditional forms of physical education, or as our games program have our treated subjects not changed very much, in which case they still belong to the population. That's what we're going to do. So just to kind of let you practice how this is going to work on an exam, just want to point out that this Excel sheet is available in Canvas. It's in the Excel sheets in the file section. And what it looks like, just kind of show you here. So that's what it looks like. And you can see that we have 4 of the 5 steps. So step number 2, for the time being, is going to be given to you, because that's going to be chapter 6 where we find out how to do that. But steps 1 through 1, 3, 4, and 5, we'll be learning how to do right now. And importantly, this is going to be how you enter it in on exams. So you put them into the yellow answer cells, and we'll go through and I'll just mention how that is done. But that's the format that you're going to see when we do this in exams. So if you want to follow along, give that a shot. That, just so you know, is going to be the way that it's going to look when we do our exam. All right, so let's read out the question here. We got the description. So a researcher is evaluating the effectiveness of a new physical education program, games program, for elementary school children. The program is designed to reduce competition and increase self-esteem. A sample of 16 children is selected, and the children are placed in the new program. After 3 months, each child is given a standardized self-esteem test. So first off, if you read this, your critical thinking brain should be going haywire, going, why after 3 months? Why not before 3 months? And then after 3 months? Because it makes the math easier, it makes the logic easier to begin with. So don't let that bother you. Seems like a silly thing to do. But anyways, they didn't measure them before, but after 3 months on the program, each child is given a standardized self-esteem test. For the general population of elementary school children, the scores in the self-esteem test form a normal distribution with a mean of 40 and a standard deviation of 8. So this is our known population. This is a widely distributed test, like an IQ test, where the makers of the test have measured the population and know that their test has a mean of 40 and a standard deviation of 8. That's the population of elementary school students. So we put them on into this program. After the 3 months, we give them this standardized test, and we find out that the sample mean for our sample of 16 students is 43.5. So is this enough to demonstrate a significant effect? We're going to assume a two-tailed test with an alpha of 0.05. So this is where the hypothesis test procedure needs to come in. Because the question of, did this treatment work for your sample, is yes. Yes, it did. Because our sample has a self-esteem of 43.5. Our population has a self-esteem of 40. You can go back to elementary school. 43.5 is bigger than 40. So we know that our sample has higher self-esteem than the population. The question though is, does it mean that the population of students, if given this treatment, would also have higher self-esteem? That's what we need the statistics for. So we know the sample, we measured the sample, 43.5. Seems to work for the sample, but will it work for the population? That's what we're going to test. So we're going to assume a two-tailed test with an alpha of 0.05. We'll get into what the tails mean later, but basically two-tailed means two lines in the sand, and we'll see how that works. All right, 5-step procedure. Let's start off with step number 1. So we got to restate the question as a research hypothesis and a null hypothesis about the population. So is there a difference between the game program student and the general student, i.e. untreated population? That's what we want to know. Is there a difference between the self-esteem of these two populations? Our research hypothesis is that it is different, that the game program does have an effect, and we can write this out as the mean self-esteem for the games population does not equal the mean self-esteem for the general population. So that's the indication that the treatment has an effect. The treatment actually does something. For the null hypothesis, we have the idea that the treatment does no effect, that our treatment has no value whatsoever. It doesn't actually do anything. And in that case, the mean of the population of students that have the games program is going to equal the mean of the general population, right? There's no increase in self-esteem. There's no difference in self-esteem. So those are the two hypotheses. And if we were doing this in a testing situation, what you would want to do, just so that we are fully aware on this, you would want to go here, and for your null hypothesis, you would want to erase the part that you don't need. So that indicates that the mean of the games program equals the mean of the general program. And for the research hypothesis, once again, you would want to, and you just kind of double click in there, you would want to delete the symbols that you don't need. And that would be the way that you would answer this particular question on a test. So we are going to continue on here. There we go. So we have our research hypothesis. We have our null hypothesis. Step 2, determine the characteristics of your comparison distribution. All I want you to know right now is that this is not your population distribution. And again, your textbook teaches you the wrong way to begin, and they get away with it because they say, well, how about we just take a look at a sample size of 1. We're going to use a sample size of 1. And when you have a sample size of 1, your distribution of sample means is the same as your population. That's why they can get away with it. And then in chapter 6, they say, well, let's switch it up. I know we've taught you to compare to the population, but now let's switch it up, and you have to unlearn that, and we'll compare it to something new. I don't like that, so we're always going to start off by comparing your sample mean to a distribution of sample means, because that's fair. You compare a sample mean to a distribution of those things, a distribution of sample means. So that's what we're going to be doing in step 2. You're going to be able to determine these in chapter 6, but for right now, I'm just going to give you the numbers that you need, and the numbers are that your comparison distribution has a mean of 40 and a standard deviation of 2. Very importantly, notice that this is not the standard deviation of your population. It's a different distribution. It's a distribution of sample means. So we have our distribution of sample means. So let's start drawing some of this stuff out. Of course. We're going to draw it out over here. All right, so we have our distribution of sample means. And it has a mean of 40, and it's got a standard deviation of 2, right? That's what we just were given. So this is our distribution of sample means. And our mean that we found, remember that the mean for our sample was 43.5, right? If this is 40, 43.5 is going to be somewhere over here, right? So that's where the mean of our sample is. And we just want to know, has our mean crossed that line or has it not crossed that line? That's what we're trying to figure out. But we can't do it yet. First thing we need is we need lines in the sand. So we're going to do that here for step 3, setting a cutoff sample score or critical value. And that's a target against which you're going to compare your results of the study. That is the line of the sand. We're going to show you how to do this very soon. But right now it's got to be given to you. And your line in the sand for this situation is called Z critical. It's a Z-score of plus or minus 1.96. And this is where we get into the Z-scores. Because if you'll notice, this comparison distribution is not Z-scores, right? It's got a mean of 40. It's got a standard deviation of 2. That's not a Z-score. So we can't work with this. We don't have an appendix where this exists, right? What we do have is we have an appendix of Z-scores. So what we're going to do is we're going to take this entire distribution and we are going to transform it into a Z-score distribution. And what that does is it takes this distribution and it changes it so that it has a mean of 0 and a standard deviation equal to 1. And now we have this in our textbook. We have this in the back and the appendix. And we're going to find out where our mean is on this Z-score distribution. Importantly for us, though, at this moment, we can now put our cutoff scores on this distribution. Because if this is 0, right around here is plus 1.96, and right around here is minus 1.96. So these areas here are your critical zones. These red tail areas here are where the samples that come from this population exist that are so unlikely we wouldn't believe them if we got them, right? These are your Bill Nye, Bill Gates, and Marilyn von Savant samples over here. It's just too extreme. This is the highly unlikely samples. This is where we're going to reject our null hypothesis. So we've drawn in these critical scores, these lines in the sand. Now all we have to do is we have to figure out where is our sample. Because our sample has a mean of 43.5. But we can't figure this out. We got to take our sample and we got to transform it into a Z-score. And we got to find out where is our sample over here. So that's step 4. We determine our sample score on the comparison distribution. We do this by changing this 43.5 into a Z-score. So all that work we were doing on Z-scores is going to pay off right now because hopefully we're practiced enough to remember that's the information we need. That's your formula for the Z-score. So we take the mean of our sample, 43.5, subtract the mean of our comparison distribution, divided by this, the standard deviation of our comparison distribution, and we end up with a Z-score of 1.75. So this 43.5 was transformed into a Z-score of 1.75. And what that means is that when we take this entire distribution and change it into Z-scores, this mean right here, that's 0. This line in the sand over here, that's 1.96. What that means is that our sample mean comes in right around there at 1.75. So you can see that our sample mean has not been a disobedient child, right? Our sample mean has not crossed that line. It stayed within the body of the distribution. So that is where the sample mean has ended up for this study. So our final move now is to figure out, what does that mean? So if the sample Z-score goes beyond the cutoff score, it did not. But if it did, we would accept the research hypothesis, and we would reject the null hypothesis. So, given that's what we would have done if it crossed a line, and it didn't cross a line, we do the opposite. So if the sample score is within the cutoff scores, if it stays in the body, then we accept the null hypothesis, and we reject the research hypothesis. And in this case, we would, again, accept the null hypothesis, which means that we decide, we accept the null hypothesis, and we conclude that the games program does not change the self-esteem of students. So all of that work, all of those years of research and trying to come up with a new program, turns out that even though it seemed to increase the self-esteem for that particular sample, it would not work for a population. We cannot generalize this effect to a population. As it turns out, we just seem to have gotten a somewhat extreme sample, but not so extreme, not so unlikely that our treatment must have done this. Any questions on that? All right. One thing that I'll mention before we go on, these two slides here, where they tell you what to do depending upon where your sample is, these are two very, very, very important slides, because I have seen students, let me just go back to the Excel sheet. I have seen students fill in their Excel sheet, and they do the null hypothesis, 100% correct. And they do the critical Z, so step 3, those are your cutoff scores, those are your lines in the sand. You would enter in 1.96 to indicate where your line in the sand is. I've seen them do that correct. The Z-score for the sample, that's what we calculated here, that 1.75. I've seen them do that correct, and then get this backwards, because this has a lot of pieces that you're juggling. This has things like, well, you have a cutoff score, you got a sample score, and if the sample score is beyond the cutoff score, then we accept it's got a lot of moving parts. So until you're rock solid, until you have done this so often that it just comes to you, I would highly recommend, not all the way back there, I would highly recommend print those slides out, or at least have them at the ready, so that when you get to step 5, you'll be able to tell. You'll be able to get this calculation. You'll be able to do this, and then just check. Is the sample score beyond the cutoff Z-score? Nope. So we're not going to do this. So what do we do? If the sample score is within the cutoff Z-score, yep. Oh, okay, I accept the null hypothesis, and I reject the research hypothesis. Make sure you're giving yourself that little kind of extra safety net until it kind of becomes automatic, because again, we're dealing with double, triple negatives sometimes here. It can get a little confusing. All right, so we conclude that the games program does not increase the self-esteem of students. We've had this, games program, we developed it, we thought to ourselves, oh, maybe this is going to help, students in general. As it turns out, not effective, doesn't really do anything. We conclude that our treatment does not work. But what if we were working with a research assistant, and they come into us and they knock on the door and they say, oh my goodness, I'm so sorry, but I scored your tests incorrectly, right? They forgot to standardize the test somehow. And in this test, you're supposed to add 1 to the final scores. And they forgot to add 1 to the final scores. So they come in and they say, I'm sorry, I made a mistake. The sample mean is not actually 43.5. The sample mean is 44.5, right? It was incorrectly entered. To our human brains, we're probably thinking, so what? It failed at 43.5. It's going to fail at 44.5. The treatment has no effect. What's 1 extra score going to do? What's 1 extra, point going to do? But let's take a look at what it actually is going to do. And this is a nice illustration of why we do the statistics, because our human brains don't really work very well for stats. So we got 44 and a half. Let's say that that was the actual correct mean. So not 43 and a half, not what we thought. Now we got 44 and a half. What does that actually do? Well, very nicely, it doesn't change a lot of the first stuff. So we're going to go through the same 5 steps, but the first step, that hypothesis, the null hypothesis and the research hypothesis, that stays the same, because we're still asking the same question. Sure, we looked at the data incorrectly, but the question still remains, is there a difference between the games program and the general student population? Is there a difference between those two populations? So our research hypothesis stays the same. Yes, there is a difference. The games do have an effect. The mean of the games population does not equal the mean of the general population. The null hypothesis stays the same. The treatment has no effect, right? That's still the null hypothesis. The mean of the games population equals the mean self-esteem for the general population. So that hasn't changed. Step 2, the comparison distribution. The distribution that we're comparing our sample to, that we're fairly comparing our sample to, meaning we can't compare it to the population, we have to compare it to a distribution of sample means, aka the distribution of sample means. And again, this is going to be a normal distribution, which allows us to access that table. Determine the characteristics of the comparison distribution. This hasn't changed, right? So we'll see again how to do this. Right now it's still given to you, but it also hasn't changed. It stayed the same so far. So not much has changed up until this point. Not much is going to change in step 3. So we still need to set a cutoff sample score or critical value. We're going to see how to do this very, very soon. We still need those lines in the sand. And those lines in the sand haven't changed. So you can see that for this type of hypothesis test, the setup is usually the same, right? The null hypothesis, the research hypothesis, the cutoff scores, these all follow a very usual, typical pattern that, doesn't change very much from situation to situation. However, step 4 is where it changes. So we got to determine our sample score on the comparison distribution. And this is where the correct number now is going to make a difference. So we go back to our z-score and how we calculate z-scores. Now we have the correct sample mean. So we have a mean of 44 and a half. We still have the same comparison distribution. We use the formula. We take our mean of 44 and a half minus the comparison distribution mean of 40, all divided by the comparison distribution standard deviation of 2. We crunch the numbers, and now we get 2.25. So look what this has done. Last time we got 1.75, and we ended up not crossing the line. We ended up in the body. But now we have, now we have 2.25. So this line here, the mean is 0. And this line here is 1.96. 2.25 is somewhere here, right? This is where our mean, sample mean, actually ended up. So now we have crossed the line. Now we have gone past that line in the sand. Now our sample is a disobedient child that went over that center line and hit their sister, right? So now we have crossed the line. So we find out that we've crossed the line. We go to step 5, and we look at our decision kind of matrix. If the sample score is beyond the cutoff score, this time it is. So what do? Well, if that's the case, we accept the research hypothesis, and we reject the null hypothesis. So we're going to accept the idea that our treatment works. We're accepting the research hypothesis. If it was the other situation, the previous situation, we would do the opposite. We would accept the null hypothesis, and we would reject the research hypothesis. So this time, with the corrected scores, one little point makes a huge difference. That's why we try to do stats as exactly as we can. Our score for the sample crossed the line, went past those cutoff scores, so we reject the null hypothesis, and we conclude that the games program actually does increase self-esteem. It actually does make a difference. It actually is effective. And with this result, we would ethically and intelligently be able to phone up schools across America and basically say, If you would like to increase the self-esteem of your students, we have a program, and it will work for your students because they're part of that population. And that's the power of psychology. All right, so that's the hypothesis testing procedure. We got 2 looks at it today. Any questions on what we covered? All right, so I was gonna go and do one more example with Harlow's monkey study, but I don't want to do that too quickly because we only have about 10 minutes left, and I do not want to zip through this. But so I'm gonna just real quick go back to the end here so that we are aware of what's going on. So first off, just to kind of wrap this up, lines in the sand, step 3, Z critical. You would enter those numbers into the Excel sheet. For your sample Z, that's this Z-score here. That's what you would enter into your Excel sheet. What is your sample score transformed into Z-scores? And then finally, for the null and the research hypothesis, you would simply delete what you don't want. So if you want to accept it, delete reject. So accept is the only thing that's left. If you want to reject it, delete accept. So reject is the only thing that's left. And in the exam, you need to have different answers there. So just like real life, you cannot hedge your bets by saying, well, I'll get one of them right if I accept them both, right? You can't do that in the real world. You can't do that in the exams. There's a penalty if they match. So just make sure that, you know, you do one or the other because, again, we need to make sure that you can make that decision. All right, so just to wrap up today, we're kind of easing into hypothesis testing because we want to make sure that we're taking our time and doing this right. So in terms of the homework, none quite yet. You kind of have some of the pieces, so you can try it out. You can go and give it a shot. But, you know, I would rather, in addition to that, if you are going to try your homework, make sure that you look over this a few times. Make sure that you go through this, go through some examples, you know, examples from the text, go through the slides again, watch a couple of the videos. Maybe go back, you know, go check out some of my previous semesters, you know, if you want to just kind of familiarize yourself with that. Because this is one of those things that kind of takes a few views until it really sinks in. So we're just going to let it sink in. We're not going to do any homework yet. We're going to have that. We're going to start that up next time. And also just, you know, this is where the pre-tests start to get very challenging. So they're still effective. Study after study has shown that struggling with the pretest, going through the pretest, even if you get it wrong, has massive learning benefits later on, especially for the exam. However, it could be very detrimental to your GPA. So do not forget about the MyStatLab study plan where you can get 100% on your pretest. So even if you try the pretest and you get nothing, right? You go through it, you give it an honest effort, but it's just beyond where you are right now. Go through it. The struggle helps. It really does. But just keep it in the back of your mind that it's not going to affect your GPA. You can pick up the mastery points by the quiz me options, the homework, you know, and the post test that you do, and still get 100% on that pretest. So make sure that you're doing that, but just know that you have that safety net. All right, we just got under 10 minutes left in this week, so if you want to call it an early day, maybe beat the snow home, feel free to do that. Otherwise, if you have any questions, call me over, but that's it for what I wanted to cover today.